What is the final velocity? You know? Negative 10. Because let's take a look at what happens here. Let's start with, how about 30 meters per second in the upward direction. So let's make a little chart here of what happens in time. At time 0, what's the velocity? 30 meters per second in the upward direction. 1 second later, what's the velocity going to be? 20. Why is that? Because our acceleration is about 10, right? We're rounding off here. Instead of 9.8, I'm going to use 10 so I can do this in my head. So the acceleration is about 10. What does acceleration mean? It means how much is the... See, we always write it as meters per second squared. Let me write it this way. The acceleration is 10 meters per second, right? Acceleration is change in velocity over change in time. So when the velocity, in 1 second, the velocity is going to change by 10 meters per second. Okay? That's what that means. So when you write it as meters per second squared, you kind of lose the meaning a little bit. But it's 10 meters per second every second. The velocity is changing by 10 meters per second every second. That's what this acceleration means. So if it starts out with 30 meters per second up, and the acceleration is 10 meters per second squared down, 1 second later, it's going to be 10. It will have been reduced by 10 meters per second. We good so far? Okay, at t equals 2 seconds, we're now at 10 in the upward direction. At t equals 3 seconds, 0. It's hit its peak, right? And its upward velocity has stopped for an instant. And then what happens? It's 0. 1 second later, what's it going to be? 10 meters per second in the downward direction, right? Because if it starts at 0 and we let go of it, 1 second later, it's going to be moving at 10 meters per second. That's what the acceleration of gravity tells us. Of course, we're ignoring air resistance in all of these calculations, right? We'll get the tools. You have to start off simple, right? Start off simple. Our model of the world right now is like this, right? Everything is a point object. There's no friction. There's no air resistance. That's our model of the world, and we're learning how to deal with that. And then in a couple of weeks, we'll be able to deal with friction and air resistance. Our model of the world increases a little bit. And around week 7 or 8, our objects don't have to be point objects anymore. Because once you give an object dimension, what can it do? It can rotate. We can't deal with that yet. But around week 7 or 8, we'll be able to deal with rotating objects, so our objects don't have to be point objects anymore. And then next quarter, you'll discover that not all objects are electrically neutral. You can give objects electrical charge. And so as we learn more, our model of the world increases and it becomes more and more realistic. But we have to start with a simple view of the world and build on that. So no air resistance. And then 1 second later, it's going down at 10 meters per second. The acceleration is down during that next second interval, and so it increases by 10, which means we're at 20. And 1 second later. Okay, so at t equals 0, it was going 30 meters per second up, and it took 3 seconds to get to its peak, right? This is on the way up. 3 seconds. So that means it's going to take 3 seconds to come down because there's no air resistance. And the acceleration is the same going up as it is coming down. So if the time is the same, then the velocity is going to change by the same amount. So whatever it got reduced by going up, it increases by that same amount on the way back down. So it always comes back to the same height with the same speed that it left, but in the opposite direction. Okay? All right. So it's a good idea to think about your answers a little bit. Make sure, think about the signs. Make sure, think about what the magnitudes. Is it more or less than what I started with? Things like that, so that in case you push the wrong button on your calculator, you get some crazy answer, you know it right away. You don't just write some crazy answer down and keep moving. Okay. Why don't we do a problem where we have we'll do 2 scenarios here. So where you're standing on the top of a cliff, and one ball gets thrown upward with speed v initial, and it goes up, and it comes back down, and it hits the ground down here. And the other one gets thrown downward with the same speed. So why don't we have half, what are we trying to find here? Let's find, I'll give you some numbers here, but we'll find V final, and let's make, let me put some numbers in here. We'll make the height of our cliff, how about 100 meters in both cases, and we'll make V initial 25 meters per second. We're going to ignore air resistance. And let's find the find V final and the time. Okay. And let's have, why don't we just split the room here. This half will do condition 1 where it gets thrown up, and this half can do condition 2 where it gets thrown down, and we'll compare our answers. So follow the follow this convention here. I want you to draw a picture. Define your origin, define your positive directions, make a table, and then go from there. Okay? Should we all pick the same origin and directions at first? Then maybe we should change it up and do it a second time with different origins. Should we do that? Let's do that. Let's define, most of you like the, let's see, where should we make the, where do you want the, or how about the lowest point in the problem to be the origin? So the ground, the bottom of the cliff? Okay, I mean there are 2 places that make sense, right? The top of the cliff and the bottom of the cliff, although you could pick anywhere. But we'll go with the bottom of the cliff here. So I'll pick, in this case, let's use as the origin, and up as positive. So that means that this is y equals 0, up is positive.